This lecture discusses the sampling distribution of the sample mean. Suppose that a variable x of a population is normally distributed with mean mu and standard deviation sigma. Then, for samples of size n, the sample mean x bar is also normally distributed and has mean mu and standard deviation sigma over square root n. This statement implies the following three properties. The last two properties always hold, no matter what distribution the population is. The mean of x bar is always mu, and the standard deviation of x bar is always sigma over square root n. The first property depends on the population distribution. Only when the population distribution is normal, the sample mean follows a normal distribution. This statement can be proved rigorously using mathematics. Here, we will not discuss mathematics. We simply use some examples to demonstrate that this statement makes sense. IQs are normally distributed with mean 100 and standard deviation 16. Consider samples of size 4. We can randomly draw 1,000 samples from this population. For each sample, calculate the sample mean. Then, we have 1,000 sample means. The histogram shows the distribution of these 1,000 sample means. It is symmetric and bell-shaped. For better illustration, we can draw a normal density curve on the histogram. The normal density curve has mean 100 and standard deviation 16 over square root 4 equals 8. The mean and standard deviation are calculated based on the statement in the previous slide. We can see that the histogram has the same shape as the normal density curve. It supports the statement in the previous slide. The distribution of the sample mean is indeed normal with mean 100 and standard deviation 8. Here we want to compare the distribution of x bar for different sample sizes. The first one is the density curve for the population. The second one is the density curve for the sample means when n equals 4. The last one is the density curve for sample means when n equals 16. We can see that all these curves are centered at 100, the population mean. When n increases, the standard deviation becomes smaller. The curves are concentrated more around its mean. In practice, the population distribution may not be normal. In many cases, we even do not know the population distribution. Can we know the sampling distribution of x bar in this case? According to the central limit theorem, for a relatively large sample size, x bar is approximately normally distributed, regardless of the distribution of the variable under consideration. The approximation becomes better with increasing sample size. The central limit theorem claims that as long as the sample size is large, the sample mean approximately follows a normal distribution. Usually, if n is larger than 30, we think the sample size is large enough. The central limit theorem is a fundamental result in statistics. Many statistical theories and models are based on it. The power of this theorem lies in the fact that we do not need to worry about the population distribution. We can always approximate x bar by a normal distribution if n is large. Let's check one example to illustrate the central limit theorem. The number of people per household in the US has mean 2.5% and standard deviation 1.4%. The first histogram shows the distribution of the number of people per household. The shape of the distribution is right skewed. Clearly, it is not a normal distribution. We randomly draw 1,000 samples. Each sample has size 30%. For example, for each sample, we calculate the sample mean. The second histogram shows the distribution of the 1,000 sample means. It is symmetric and bell-shaped. The normal density curve on the plot has mean 2.5 and the standard deviation 1.4 over square root 30 equals 0.26. This example shows that the distribution of the sample mean is approximately normal, even when the population distribution is quite different from normal. This slide shows more examples. We have three different distributions. The first row shows their density curves. The first distribution is normal. The second one has a reverse J shape. And the last one is uniform. In the remaining rows, we show the distribution of sample means for different sample sizes. For the first column, because the population distribution is normal, the distribution of sample means is always normal, no matter what the sample size is. The uniform distribution is closer to normal than the reverse J-shape distribution. Therefore, when n equals 10, the distribution of the sample mean in the third column is already very similar to a normal curve, but the distribution of the sample mean in the second column is still quite different from normal. However, for all of them, when n equals 30, the distribution of sample means is very similar to normal. The graphs tell us if the population distribution is similar to normal, the normal approximation can hold accurately even for small sample size. If the population distribution is quite different from normal, we need a much larger sample size in order to achieve a reasonably accuracy in normal approximation. Let's check one application of the central limit theorem. The birth weights of male babies have a standard deviation of 1.33 pound. Determine the percentage of all samples of 400 male babies that have mean birth weight within 0.125 pound of the population mean birth weight of all male babies. Let mu be the population mean. This problem asks for the probability of x bar greater than or equal to mu minus 0.125 and smaller than or equal to mu plus 0.125. According to the central limit theorem, x bar approximately follows a normal distribution with mean mu and a standard deviation 1.33 over square root of 400. Here, 400 is the sample size. The 400 is much larger than 30. So then we think this sample size is large enough, and the central limit theorem is applicable. Therefore, we simply treat x bar as a normal random variable to evaluate this probability. We need to first calculate these scores, and then find the probabilities corresponding to these scores using the standard normal table. The final answer is the difference between these two probabilities. The z-score is calculated as x subtract mu and then divided by standard deviation. Therefore, we can calculate the scores as minus 1.88 and 1.888. The probability is 0.9398. Therefore, 93.98% of all samples of 400 male babies have mean birth weight within 0.125 pound of the population mean birth weight.